Hi my friends, today we study this mechanism rotation to sliding, and you can download all the components by clicking the link. I've posted it in 2016 on GrabCAD, and there are questions which I want to answer. Take a look at the functionality. Generally speaking, you can download assets by using the link presented in the last line of the description in every tutorial. Well, we start with creating the assembly, placing the support, grounded at origin. This is the support. I don't like this plane, so I go here and apply visibility. You see, all you download from that links are parts made with Inventor 2014, very old. Being so old, you can edit the downloaded parts and assemblies no matter what Inventor version you use, if it is 2014 or newer. This is an advantage for you. For instance, you can modify this very part to apply the surface finishing to some faces of it. Okay, double click on the part to edit a part, not an assembly. Select both faces and still polished. Now they are like the other. Return to the assembly, F6, and now it seems to be so dark, I don't like it. We can create a new ambience or environment by selecting two lights and settings with some adjustments. Here I make this about 28, this about 10, 11, 11. You see, this is changing. 70, the general brightness is changed. And go to the next light, which is gray. This is the problem. I select white to be bright in the image, and another two changes. 44 is very good, and the last and the most important is this one. Look here, to be around 60, 63. Save and close. You see, now we have another brightness, and this is okay. We like what we see here. Good. We continue to add parts, the disc and the shaft 10, diameter of 10. Okay, we select disc to make this plane not visible, and then constrain. Insert aligned this end with this face, yes, to have this situation. And also insert excuse me, apply and insert with the other solution. What to insert? This face and axis with this. Yes. Okay. Now we can rotate this. We see here that there is a key. Yes, this is the input of this mechanism. Another component is the long shaft, this one, which we want to be placed here. Also applying constrain, insert, solution 2 of this circle to be placed here. Okay, then place the curved lever, which is this one, but we have to take care with something. You see there is a fillet all over this part. We don't need to have this fillet because we'll use dynamic simulation, and we have problems if we still keep this fillet. So we edit the part and we select fillet. You see it's all over, and we delete it, or we can suppress, delete. Yes. Go back to the assembly, constrain, insert this circle with this, apply. Now if we make movements here, we see that something is missing. What is missing? A roller between these two parts. Let's place that roller. Place a roller here, and I want to eliminate one chamfer in order to use dynamic simulation, as you will see. Double click on chamfer, and we select this with shift. Okay, good. You see this end does not have any chamfer. Finish modification and constrain with insert of this face with this face. Okay. Now if we apply here a constraint, which is transitional between this face and this face to be always tangent. Okay, F6. Now if we rotate this, we move also the lever. You see? Good. Now we save this assembly in this situation. Save as RTS, rotation to sliding. Save. As you can see, because we changed some parts, it appears a migration from Inventor 2014 to 2021 at myself, and to you is 21, 20, any release of Inventor you have. Okay, we continue with adding other components like this one, the lever, simple lever, and also the slider. We constrain them, constrain, insert this face with this face. Okay, now I turn this. When you cannot do something, you ground an object like this one, grounded, and then you can rotate freely the part and unlock this. Next, constrain, insert this with this. Yes. Apply. Again, this must be, oh, it is not good, but no problem. We go here, we erase this constraint, and we use free rotate for turning the part as you see now. Then constrain, insert this major circle with this major circle. Okay, now we have what we want to have. Now I make something which will be not good, but you have to learn from mistakes. Constrain, face, on, face. Okay. Oh, another mistake. Yes, another mistake. This was placed not good. Once again, this insertion to be deleted. We move a little and we apply again, insert, the two faces. Okay, now everything is okay. Yes, we have all we need. Not all we need, but enough to make this and this. Yes, good. What is missing? The two shafts here and here. For the simulation this is not important, but I want to place them because they contribute with their masses. Yes, we don't want to lose this contribution. We place this short shaft in 2 instances. Constrain, insert, solution 2, this is here, apply, and the other is here. Okay, F6. Now the movement is the same, no problem. You see a mid position here. Good. Now let's save. Yes, save. Okay, now we have no migration because we didn't change any component, and we apply dynamic simulation. We receive a message. You were prevented about this. The mechanism is over constrained by 1 degree. Use the repair redundancies command if automatic joint creation is not active. We have active this situation, and we see here automatically convert. Well, let's see what is the situation. We have here a tool, mechanism status, and it shows how many redundancies are and the other degrees of mobility and so on. If we activate this button more, we see where is the problem. The problem is at revolution 3. You see there are 6 degrees at any joint. This is a joint. Revolution 3 is a joint. And the 6 degrees of freedom are okay except Rx, rotation about the axis X. Of what? Where is X? We close this window and we select the joint, and you know this is with 1 arrow is X, with 2 is Y, and with 3 is Z. The problem is with the rotation about this axis, curious axis, when we look at the joint. The joint is between this fork and this lever. How can appear a rotation about this axis? Well, the problem is not here, the problem is here. When we placed this object on this face with mate, we use mate, we constrained 3 degrees of freedom, 2 rotation and 1 translation. Translation on Z, this Z, and rotation about this axis, and rotation about an axis parallel with this. Yes, we don't need this because that degree is constrained here. We cannot admit to have the same degree at the same part, this part, to be double constrained, in fact. And what can we do? We have to use here not 3 but 2 degrees of freedom with a mate. Let's see how to do this. Finish dynamic simulation. Yes. take a look at this part, and select mate. This mate is for 3 degrees of freedom. Delete it. Now we can move this, yes, and rotate, but take care that this rotation is constrained, yes, only not this, excuse me, not this rotation, but this one, about this axis. And what should we do? We apply constrain between this face and not this face, but this line, yes? Okay, the other rotation about this axis, this rotation, is already constrained by the joint, this joint. I suppose you understand this. I'm not so good in English language, but I hope you understand. The movement is the same, not any change here. Yes, look. Yes. Let's see what happens with the dynamic simulation. Now click, and we have not any message because there are no problems. Let's see. Nowhere is a problem. No mark here about that over constrained degree. Good. Finish dynamic simulation and save without any migration here. Okay. Now we think about what questions I mentioned at the beginning. One question was how does this mechanism behavior when we apply a force somewhere on this plate. You need to imagine that these holes are used to place here something and to use that something for some operation. One of my friends told me about using a knife to cut the ham. Yes, okay, this can be used for cutting ham with it. But what about forces here? We must use dynamic simulation for this. But I have to modify this part to have a point for placing a force. Double click on this, click on this face, create a sketch, place a point here, the same horizontal, vertical, not so, the same vertical with the this midpoint, and the same horizontal with this midpoint. Yes, normally this is the position, or this, to have vertical and horizontal in a real position. Finish sketch, hole, and we apply metric 6 normal pitch hole with 12 millimeters depth and 8 millimeters depth for the thread. Okay, return, and we are now back to the assembly. Environment, dynamic simulation. You see here all the development of elements in the browser, and we apply gravity to have a real mechanism by using this edge, which is vertical but the other direction. Yes. Okay, click to hide the arrow, and now we start for 1 second the movement. Oh, this is not good. The rule is that dynamic simulation converts only constraints that have to do with degrees of freedom, such as mate or insert, but does not convert constraints that have to do with position, like angle or transitional in our case, as you know. We have to substitute that kind of constraint with joints, yes? This is why we need to add a contact joint. Click here, not special, not rolling, not sliding, but to the contact. To know more about this technique, you have to watch my former tutorials number 44 and 45. We select a face. This is the face or an edge, not only faces. And then an edge. Yes, we look now to see how is every arrow placed here. You see the Z arrow is towards the center of this slot for the slot, and toward the slot for the roller. It is good. We want to be in contact this with this. Okay, and I hide the vectors, and we take a look, frontal or side look, and now again 1 second of movement. Oh, good. This is all. Let's change this, but the construction mode must be chosen to 10 seconds start, and we see all the movement here. Okay, now we have to impose a rotation of this, because this is the input element for moving the mechanism. To do this, we select the joint between this disc and the housing. Let's identify it. It is a standard joint, and it is this 5, number 5. If I select this, we see vectors used in this joint. Yes, it is here. The insert with contact here is changed now, is transferred to a joint, a standard joint. We right select properties, DOF 1, the only degree of freedom, because the other 5 were constrained by the insert contact converted to revolution 5. We don't use initial conditions, we don't use joint torque, we use imposed motion. Enable imposed motion, and we select the graph 0 to 10 seconds. We want to have, say, 100 degrees per second, the speed, rotational speed, in the first second. Let's change this in 1 second and this in 100 to be round for you to understand better. You see the first 1 second is for starting the rotation of the disc. I use the wheel of the mouse to make zoom here and click on the wheel to move the graph in the space. Okay, now we know that the disc will be moved from the start with 100 degrees per second. Let's see what happens. Start. Very nice. Yes. We move back and we start again to see the movement. The imposed speed is doesn't consider forces or moments. This is why it rotates without any interruption or friction or anything when you apply imposed motion. Let me detail this. I'll add a force here to see what happens. Force placed in the center of this with a value of say 100 newtons, which means 10 kilograms. The direction is along this line and the orientation is to the left. We want to place it to the left. Let's start again with the dynamic simulation. Nothing is changed. The same rotation, the same situation. Okay, now we want to substitute the imposed motion here with a torque. The imposed motion is fixed. Yes, 100 degrees per second, and nothing changes this value. If we substitute it with a torque, we'll have a torque against the force multiplied by distance. To have an idea about the situation, let's measure some distances M is the shortcut between the center of the disk and the center of this circle. And if we click here, we see that the torque applied because of that force is 100 Newton multiplied by 135 millimeters, 13,000 Newton millimeters. This is the torque created by that force. So we have to place torque with this orientation or direction comparable with the other torque to see that they work one against the other. Yes? Good. Escape. Go to the imposed motion to disable it. Yes, now we don't have any movement of the disk. And what happens? Well, only the force action now. Let's see. Yes, there is an inertia, and that's all. We are in construction mode now, and we'll apply a torque to what? To the disk. Let me show you the direction with a value of 1000 for beginning, not 10,000, to see what happens. Yes, what is the vector? This is the vector, but with the other direction. Okay, again we look frontal and we start this. You see, the force is major in this environment, and the torque does not mean something. Double click on torque and I change this with 10,000 Newton millimeters. Yes, now they are comparable, I suppose. Yes, they are. What is the conclusion? The conclusion is that we can apply either an imposed motion or a torque to rotate the disk. The first is immutable, so that the movement remains unchanged no matter what other force or torque opposes it. And in the other case, there is something natural, a torque against a torque that balances each other. Okay. Now let's study a little about the quantitative aspects of this simulation. We open again the dynamic simulation. We run the whole movement. This is the whole, but we wait to the end, 10 seconds. Having this all data memorized by the dynamic simulation module, we open Output Grapher and we take a look at the external loads, the torque, which is a moment, in fact, and it has the value, as you can see, it appears here, 1 multiplied by 10 at the power 4, which means 10,000. Yes, 10,000. 10,000 what? Newton millimeters. You see here, Newton millimeter is the unit. And for the force, the value of the force, which is, let me enlarge this graph, which is Newton. How much is 100? 100 is from 0 to this red line, while the moment is very great, but there are other things. We have to multiply 100 with that 135 millimeters to obtain the real value of the couple or moment to balance this value. Now, if we make something else, we apply trace velocity for this point. Yes, I don't see the mark. Okay, now it is. Okay, now we can see the graph of the velocity by clicking this V, and you see here the velocity. Let's start again to see what is the dynamic of this graph. That's all. Yes. We go to construction mode. I want to move this to have all the visibility. I move this a little and I change this to 2 seconds. You see, 1.25, 2.5. We need only this duration. So I place here 2 and I make this not visible, but not now. Let's start all, and you see the velocity is presented with a graph. If we uncheck this moment and we go back to see the real movement, we see what happens. If we want to be more precise, we can change this, but when it is in construction mode, to be realized in slow motion, but not slow motion, more images per second. It seems to be slow motion. Look here. Yes? Now the data are collected by the dynamic simulation module, so this is why it works a little. We stop here. We go back. We change for 1.5 seconds. We start again to create the data. and you see how is the behavior of this mechanism. The trace is here, 0. The force is 100 and the time is 1.5 seconds. You can click anywhere here, you know this, and use the arrow key on the keyboard to the right and to the left to see other values in other moments of this movement. The speed is greater here, smaller here, and smallest here. You have all the data to control this simulation. There is no time to see all of them, but in time I'll try to present the other elements of dynamic simulation because I really like it, and you, my friends, enjoy when you see this, I hope. Good. This is all for today. Thanks for watching. Bye bye.